Okay, so here is example 2 to understand VC dimension. Example 2, so this is the hypothesis class, this is what I am going to call as APR, hypothesis class. APR stands for axis parallel rectangles. Think of this as a generalization of the interval hypothesis class, right. So, this is basically the set of all axis parallel rectangle classifiers, and I will tell you what that means in a minute. Okay. So, what is an axis parallel rectangle classifier? So, let us say you have a 2D in R2. Okay. So, what is an axis parallel rectangle? So, there are two axes, the x axis and the y axis. A rectangle which is whose length and breadth are parallel to the axis is an axis parallel rectangle. For example, this is an axis parallel rectangle. Now, of course, imagine this as an exact rectangle, I may not have drawn it exactly. So, what is the classifier itself? So, the classifier is just going to label 1 here inside the rectangle. Earlier it was an interval, now the interval is kind of generalized to a rectangle in 2 dimension, that is all has happened, right. So, it is basically plus 1 here and then it is 0 elsewhere. This is one classifier. Of course, there can be, of course, this also has infinite, right. So, it is clear, easy to see that this also has infinite hypotheses. So, this is another one maybe where as long as it is axis parallel, does not matter where it is situated. So, this is going to say plus 1 inside, oops sorry, this is going to say plus 1 inside, 0 elsewhere, yeah, and so on, right. So, you have every axis parallel rectangle. Now, question is what is the VC dimension of HAPR? So, we can, how do we argue this? So, we can look at the same game thing that we were talking about. So, we can start with player 1. If I give you just 1 point, I mean, let us quickly see, if I just give you 1 point, well, nothing really changes, right. So, I can always put either this axis parallel rectangle to, if my label is plus 1, you can give me this. If I say it as minus 1, you can give it this. So, 1 point, you are fine, right. So, you will win, right. So, this is n equals 1. Now, when n equals 2, so now you can give me 2 points, any 2 points, however you give me. Now, well, these need not be, I mean, these can be anywhere, right. So, they will always be on a line, but they can be anywhere. Now, so depending on what label I give you, right. So, if I give you 1 1, then there is this rectangle which has both of these, enclosing both of this. If I give you 0 0, then maybe there is some other rectangle. If I give you 1 for this and 0 for that, there is a rectangle. 1 for the bottom one and 0 for the top one, there is another rectangle. So, no matter how I give you, you will always win, right. So, n equals 2 is also, you have a winning strategy. Now, n equals 3. Now, let me make a point, important point here. Let us say you give me these 3 points, right, and so these 3 points which lie on a line, right. So, let us say you give me these 3 points. Now, what I will do is I can label them as plus 1 and 0. Now, if I do this, then no matter which rectangle encloses the plus 1s, it also has to enclose the 0, which means that you do not have a winning strategy, right. So, because I can always say the middle one is 0, similar to the interval thing that we spoke about, right. So when n equals 3, if you give me these 3 points, then I have a winning strategy. But let us pause and ask, does this mean you do not have a winning strategy? Well, remember, so far it did matter which set of data points you picked. No matter what data points you picked, no matter what labelings I gave you, you had a winning strategy. But now in this case, it becomes important what data points you pick, right. So that is why in the definition of VC dimension, we are not saying for all choices that you make. You also have to be smart about picking your choice. If you do not give me a smart choice, if you give me a choice like this where 3 points are linear or collinear, then that is not a smart choice, because I can break you, right. So I can give you a set of labels for which you cannot give me a rectangle. But if you are smart, then you probably will not run into this problem, right. So it's important that player 1 chooses the points carefully as well. So far that did not make much sense, but from now on it is going to make sense, right. So you have to choose your points carefully, such that you know that I am going to break you, and you have to keep that in mind and choose the points, which means that you would never choose 3 collinear points, right. So what else would you do? Well, you would choose some points which are non-collinear, maybe something like this. Now in this case, if I say +1 0 +1, you still have a winning strategy, right. So because you can give me this rectangle. Only if they are collinear we run into problems. Even if they are slightly non-collinear, still I can kind of fit a rectangle inside, because there are infinite possible rectangles in my bag, right. So which means that you have to be smart about picking the data points also, right. So the VC dimension argument is there exists a set of points, and here is a set of points, right. So not for all set of 3 points, there exists a set of 3 points for which no matter no matter how I label, you will still be able to produce a classifier, right. So if I label it differently, I can always put each of these separately as 1 and the rest are zeros. I can club these 2 things using this rectangle, club these 2 things I have already done, club these 2 things using this rectangle, which means this alone will be 0. Of course, I can put something else outside which will make that 0. I can of course create a big rectangle which has all of these as 1, right. So which means no matter what combination I have, I give you, you still have a winning strategy, right. So we have to be very careful about how the definition is, right. So it's not for all data points, but some carefully chosen data points. Okay, so that is n equals 3. So now n equals 4, how would you give me? Well, again, if you can pause and think about this, how you would give me 4 data points. Let us say you give me in some kind of a diamond thing like this. Now I have 16 possibilities. I am not going to go through all the possibilities, but it suffices. I mean, you can try this out yourself so that you can pick any subset of these points and then they can be labeled as 1, right. So maybe if you pick this the vertical ones and the right hand side one, so then there is a rectangle like this. If you pick the bottom 3, then there is a rectangle like this. If you pick the top 3, then there is a rectangle like this, right. So and it's not hard to see that no matter how I give you the labels, there is a rectangle. Of course, there is a big rectangle for all 4, there is one outside all 4. So even if you pick 2, I mean, does not matter which 2 you pick. So this 2 has a rectangle, this 2 has a rectangle, these 2 have a rectangle, this 2 has a rectangle, and so on, right. So all pairs of 2 have a rectangle, all pairs of 3 have a rectangle, and so you can you have a winning strategy if you pick these 4. Now let us look at n equals 5. Now n equals 5 is the interesting case where no matter how you pick these points, right. So no matter how you pick 5 points, there is going to be one point which will be enclosed in the rectangle of the other points, right. So if I draw the tightest rectangle of 4 points, so you can put 5 points anywhere on 2-dimensional space, what I am saying is that there will be 4 points for which if I draw the tightest rectangle containing these 4 points, the fifth one will be inside this rectangle. For example, I just arbitrarily put these 5 points. Let me mark them harder so that you will see what I am saying. Now, what I am saying is that if I pick this one, this one, this one and this one and try to draw the tightest rectangle containing these 4, what rectangle would that be? Well, that rectangle is going to look like this, right. So, it is going to be as tight as possible. So, I will not waste any other extra space. I mean this may not necessarily be linear. So, this can be here as well, right. So, it does not matter, maybe I will put it right. So, this, and I am also including this in my tightest rectangle. So, this is the tightest rectangle that contains these 4 points, and now the fifth one is inside this rectangle, right. So, convince yourself that no matter how you pick 5 points, this will happen, right. So, it will happen for some 4 points, right. So, the tightest rectangle containing some 4 points will necessarily have the fifth guy inside that rectangle. And the moment I observe this property, what I will do is I will make these guys as +1 and this as 0. Now, because the tightest rectangle is, I have already seen the tightest rectangle. So, any rectangle that makes these 4 guys as +1 will contain the tightest rectangle. And because the tightest rectangle will also say this inside point as +1, but because I have labeled it as 0, I have a winning strategy. This is the equivalent of saying that if you have an interval, if you have 3 points in an interval, there is a middle point, a point inside that interval, right. So, the equivalent of that in the rectangle case is that the tightest rectangle in 2D for 5 points will contain, I mean for any 5 points in 2D, there exists a set of 4 points whose tightest rectangle contains the fifth point. And so, by that observation, by that geometric observation, I have a winning strategy in this case, right. So, which means that no matter how you give, right. So, now you can be as smart as you wish, right. So, what I am saying is no matter how smart you are, I will still be able to beat your strategy, right. So, that is what this is saying. So, which means that then our conclusion is that the VC dimension of this APR, axis parallel rectangle class, is 4. Why? Because till 4 you have a winning strategy, and the maximum value of n for which you have a winning strategy is the VC dimension. That is how we have defined it, right. So, yeah.